So after demodulation, we've got the demodulation of AM. Okay, so demodulation or detection is basically the process of recovering the original message signal from the received modulated signal. So this happens at the receiver side. Okay, so what you see at the input of this block is the modulated wave, amplitude modulated wave. Can somebody tell me what kind of modulation is performed there? It is called under modulation. Okay, yeah. So once you receive it, a demodulator will detect the modulating signal there, which is called a demodulated signal. So there are two different types of demodulation. One is square law demodulation, other one is called the envelope detector. So second type is widely used in all practical applications whenever AM modulation is performed. So let us see how it looks like. So this is the circuit diagram of a square law detector, where we at the input side we have got a square law device, or it's nothing but a nonlinear device, and we already know the mathematical model for it. So if the input is v1 of t, which is a modulated wave, v2 will be some scalar a times of v1 of t plus b times of v1 square of t. We'll limit ourselves to second degree because higher orders will not be contributing too much. Okay, when this is passed through the square law device, what we get is an output which is v2 of t. When you expand it after substituting for v1 of t, which is your AM signal, which was dealt earlier right here, if you can see this equation here, this equation what is written at the end for v2 of t becomes the input to the signal here, which is, after expanding, you get it as equation number 2. So in order to extract the original message signal, we have to pass the signal what we have received here, which is v2 of t, the last equation, equation number 2, through what is called low pass filter, which is shown in the circuit. So I should choose an appropriate RC values so that I get the output as some scalar constant m times of b times of AC square times of x of t, which is your modulating signal. So this is the whole idea behind performing the demodulation. So envelope detector is a much more better practical circuit to demodulate the signal. So we'll see how it works like. So input will be EM of t, or sorry, S of t, which is the modulated wave, and you pass it through a detector diode, so which is nothing but a square law device again, and you have the same RC network. So conceptually both the circuits are one and the same, but the way we are writing is slightly different. So what happens, a standard wave, AM wave, is applied as an input to the detector. In every positive half cycle, the input diode is forward biased. This will basically charge the capacitor C, and when the capacitor charges to the peak value of the input, diode basically stops conducting. Capacitor will have to basically discharge through the resistor R between the positive peaks. Okay, so if you basically observe this wave, what happens is, so initially during the positive half cycle, the very first positive half cycle, you can expect the capacitor to charge to the peak value. Okay, and later on what happens is, let me use a pen here. Okay, so during the discharging process, you keep the resistance, this particular resistance, in such a way that resistance becomes very large. So this R value what we choose here is a very large resistance value. Okay, we purposefully choose this resistance value which will be very large. Okay, so based on that, what we observe is, even though the charging process has happened, capacitor is never going to discharge. So when this process is attained properly, so what we get is a kind of signal like this. Let me write it and show it to you. Hold on for a second. Okay, so capacitor will never discharge. Again, the next positive half cycle will appear. Capacitor charges again to the peak value, it goes up, and finally the negative part will also come. So what we are able to see is the output waveform becoming a sinusoidal signal, which is low frequency, which is nothing but your modulating signal. So this is what is going to happen. Okay, so this process basically continues, and the capacitor charging and almost no discharging will happen. So this waveform what is shown here will clearly show the process what is explained then. So diode goes to on condition and discharging will be very minimal, and finally the envelope gets detected. Okay, so this is how basically the envelope detector works. So there is a mathematical definition also given to it. So a times of m of t, a plus m of t times of cos omega ct becomes the input to the detector. So we have written the equation for Vs, which is nothing but the modulated signal, and later on I can represent the diode with that equation which is written in the second part, which is this. Okay, right here. Okay, so later on what you will have is 1 by pi into a plus m of t and all other higher order terms, which all gets eliminated through the low pass filter. So the same explanation is given even in this case, identical to that of a envelope detector. Okay, so this is what it is. So now if you basically try to see the equation of an AM, so we'll slightly move ahead. S of t is equal to AC cos omega ct plus AC by 2 into cos of omega c plus omega m whole multiplied by t plus AC by 2 into cos of omega c minus omega m whole multiplied by t. So here the carrier component basically remains constant and it does not convey any information at all, correct? If you see the second and third component, omega mt component is there, which is our actual modulating signal. So our interest is only on those components or those terms which contains omega m within it. But the first term, AC cos omega ct, has no omega m at all, isn't it? So what we are trying to do here is, but if you try to see the total average power, the carrier component basically consumes more power compared to the other two components. If you try to find the average power, if you take the first term as it is, so what is the total power consumed by the first one? See here, the total power consumed by this fellow is EC square divided by 2. That becomes the average power. How about this? It will be EC square divided by 4. Correct. And you will also have M there. Anyways, we have missed out this M. So M comes into picture there. So it will be M into EC square by 4. And this will also be M into EC square by 4. So what we observe is the carrier component consumes more power but does not convey any information at all, which is of no use for us. So that is why we always try to suppress the carrier and try to convey only the other two components, which are low and upper sideband components. And when you do that, you say you basically are performing